let's say now that instead of having a single input, single output system, or a multi-input, single output system, we're now going to have a multi-input, multi-output system. Now this represents most systems in the real world, because for any system there might be multiple things that affect how our system behaves, and there may be multiple outputs that we can measure. So if we have a single input, single output system, our transfer function is going to be the output over our input. If we have a multi-input, single output system, our transfer function is our output over the desired input, and we're going to set all other inputs equal to 0. Now, if we have a multi-input, multi-output system, our transfer function is going to be our desired output over our desired input, both in the Laplace domain. We're going to set any non-interested inputs equal to 0, but we're going to have to algebraically isolate our output. So we can imagine if we had a mass spring damper system, we could say that one output would be one output could be the displacement of the mass, but another output would be the force that is stored in the spring. So maybe we want to see what stresses are in there. Now, if we set the displacement equal to 0, that's going to also set the forces equal to either 0 or whatever they are at static equilibrium, but that's going to distort our output too much. So we can't just set other outputs equal to 0, but we can algebraically isolate them in order to come up with a transfer function. So let's look at an example, and we're also going to look at hydraulic systems. So these are mechanical and fluid systems. Now, hydraulic system, we can first look at a damper, where we have a force input to our system, and the device is going to be slowed based off of the fact that there is a mass operating within a fluid. The fluid can travel through a small channel within the mass, but we'll see how that influences the force. So we have that there's a pressure from the force, which is going to be based off of the difference between the pressures in channel 1 and channel 2, so P1, P2. And if we have our free body diagram there, it's a mass with two forces on it. So it's the force applied minus the force of the piston. And that force from the piston will be A times the area times the difference in the pressures of the two chambers of the fluid. And we could analyze it through mechanical, and we can also analyze it as a fluid system. So in a fluid system, the change in our pressure over the resistance is equal to our volumetric flow rate. And we calculated that before. It's just going to be a function of the viscosity of the fluid, the length of the pipe, the diameter of the pipe, and our volumetric flow rate is equal to the area times the velocity of the mass, x dot. So we can combine these two systems and say that our my double dot is equal to the force applied minus a squared times r, where r is the resistance of the fluid through the pipe, times the flow rate times the velocity of the piston, so y dot minus z dot, where z dot is the velocity of the housing. And for a small mass, so we can say that the force is going to be equal to a squared r x dot, which is equal to cx dot. So that's the force that we have from a damper, because a damper is a hydraulic system. So we see that the force from a damper is cx dot, and it resists velocity instead of resisting displacement like a spring does. Now if we look at a full-on hydraulic system, then this full-on hydraulic system, we might have that we can operate a wheel using differences in pressure, where we can control the difference between pressure 1 and pressure 2, and we want to see how that's going to affect a wheel turning. Now in a mechanical system, we can say that there is the force from the pressure and the force of friction if we have a no-slip condition, which we're going to assume we do. And as the wheel rotates, it will rotate either with theta or x, where the relationship between theta and x is equal to theta r. So the sum of our forces is going to be the force from our piston minus the force of friction, and the sum of our moments is just going to be based off of that friction force, which means that we can have the sum of our forces just in terms of our mass moment of inertia and the force of the piston. Now we want to look at the fluid side of this. For the fluid side, we have the volumetric flow rate is going to be the same whether it's going from P1 to P3, from P3 to P4, or from P4 to P2. And I've wrote those two pressures in. We're not going to care about them. They're outputs that we do not care about, but they are going to influence how our system behaves. So we're going to need to work with them, much like we've worked with a dummy variable with springs. Now, our volumetric flow rate is going to be equal to the difference between the pressures divided by the resistors of the valves, and it's also going to be equal to A times X dot, just like the example on the previous page. Now, using these two equations, we can now represent P3 and P4 in terms of P1 and X dot as our variables, and we can represent the difference between them in terms of P1, P2, and here we have A R1 plus R2, and we need to add an X dot there. Let's see if I was smart enough to do that. I was. There we go. And we can now combine these two equations and have a transfer function of X in terms of P1, and if we wanted X in terms of P1, P2, it would just be negative A. But you can go through, look over the notes, I'll have them below this video, and we now see that we have X over P1 for our transfer function, and that is a, whoops, here is an error here. There should be a little squared term there, because here we had the double dots, so that should be an S squared. Okay, but that would be how we would do the transfer function of a hydraulic system.